All righty. So we're going to pick up now where the earlier class left off, talking about light and with Kirchhoff's laws. So just to recap, Gustav Kirchhoff had this experimental setup with a hot bulb, and then there were three sort of different mechanisms that or three different directions that he used to capture light. He had light travel straight from the bulb through a slit in a wall. That slit allows a little bit of light to pass through, and that light got split up by a prism, cast against a screen, and you saw a continuous spectrum, right? And the idea is that something called a black body, which we'll address in 2 or 3 slides, like an incandescent light bulb, emits all wavelengths, and you get what's called a continuous spectrum. So you'll notice in number 1, that picture has no breaks in the spectrum. Then, if you were to take a hot bulb and you had that same sort of like slit where light could pass through, go into a prism onto a screen, but before the light reaches the slit, it has to first pass through this gas. Well, what's going to happen is the gas ends up absorbing some of the light. Very specific wavelengths of light get absorbed. And when the remaining light that passes through gets dispersed and cast on a screen, you notice that there are certain colors that are missing. And that's what you see here. This is called the absorption spectrum, right? Showing which wavelengths were absorbed by gas. And then there was one final setup in which no light from the incandescent bulb passes through the slit and goes through the prism and gets separated. Instead, we're only looking at the light coming from this hot, low density gas, the same one that was used in the previous trial. And without a light source behind it, you don't get a continuous spectrum. You don't get an absorption spectrum. Instead, the only light that makes it through is the light being emitted by the hot gas itself. And the colors that are emitted by it are the same as the colors that were missing from the absorption spectrum. And you can see here how the absorption line spectrum and the emission line spectrum look like inverses of each other. Right, so we talk, and astronomers talk a lot about spectra, right, which is just like a, we're just looking at the light coming from an object. And so so here's what makes these spectra so important, or like these emission line spectra. Every single element has its own unique spectra, has its own unique spectral pattern. It's like how we each have our own set of fingerprints, right? Nobody's fingerprint is like mine, and nobody's fingerprint is like yours, right? It's unique. And for atoms, every single element has a unique fingerprint. That being said, hydrogen on Earth and hydrogen on Mars and hydrogen at the sun should all emit the same spectra because it's hydrogen. But that's really important, because if we know what the spectral pattern is for a certain element, and then we point our telescopes into space and we notice, hey, that star over there has a fingerprint that looks like it contains hydrogen in it. Well, it probably does contain hydrogen, because you're getting that from the spectral patterns coming off of that star, right? And we know, and we're able to make that connection to hydrogen because we know hydrogen's spectral pattern, right? So if we know all of the different elements' spectral patterns, if we know their unique chemical fingerprints, we can identify it elsewhere in space. So you can see here how these fingerprints look a little bit different. Here's hydrogen, there's sodium, it's got the infamous double yellow lines, helium, neon, which is all in the yellow, red, and orange zone, and then mercury, which is sort of interspersed. And then, maybe we look at some even more these are, I think, actual images. These are actual images of emission spectra from different objects. And if we were in person, this is a slide from a previous semester. If we were in person, we would actually be doing an activity right now, a lab, where you put on these special glasses that take the light coming from a source, and it actually splits it up into the different colors coming off of it. So you can identify the spectra, right? You can like look at a thing. You can look at a hot gas in a tube. You could compare it to this template and then figure out what element you're looking at. Okay, so let's move on, all right, to thermal radiation, which is our conversation on black bodies. So a black body is something that absorbs and re-radiates all light and energy. And the amount of radiation that it emits is going to be based on its temperature. So the sun, for example, is an approximate black body, meaning the sun absorbs all colors of light and re-radiates all colors of light. And so black bodies are usually associated with a continuous spectrum to a degree. So the sun is an ideal black body. Planets are ideal black bodies. Even though they don't emit their own visible light, planets emit their own infrared light. And even you and me, we're all ideal black bodies by this definition, because we radiate a continuous spectrum of, we absorb rather and re-radiate all energy, right? All wavelengths. And so the amount of so this is where the important connection comes in. The amount of radiation that an object emits is very closely tied to its temperature. So based on an object's temperature, we can sort of predict what or how much light it will emit. For every different frequency, we could predict what its output would be. We could also predict or calculate, I should say, not predict, but we can calculate, for an ideal black body, given that it's at a certain temperature, what color would it look? Which wavelength of all the different wavelengths it's emitted, which one would be the strongest? We could figure that out. So here in the United States, we are very used to describing temperature in terms of degrees Fahrenheit. Elsewhere in the scientific community, we describe temperature in terms of degrees Celsius, and in some cases in Kelvin. Kelvin doesn't have degrees associated with it, it's just Kelvin. And when we talk about absolute zero, the lowest possible temperature that there can be, absolute zero refers to zero on the Kelvin scale. There is no negative Kelvin. Right? Zero is as low as it goes, unlike Fahrenheit and Celsius, which can go below zero. So the Kelvin scale is based on absolute zero. And I just have here in the, excuse me, I have here at the bottom, the temperature that water freezes at and boils at in both Kelvin and degrees Celsius. Okay. So let's make more sense. Let's make sense of this, and then we'll make more sense of it. So there are two laws, and those laws are are both expressed in the picture, but also in numbers 1 and 2 at the top, right? So essentially, we need to know two things. One, the hotter something is, the more light at all frequencies it will emit per unit area. What does that mean? So something that is like if you compare the sun to your body, right? Your body is not hot enough to emit light at all frequencies for every unit of area that you have. But the hotter you get, think about like an electric stove, right? When an electric stove is cool, what color is it? Gray, black, right? It doesn't really have a particular color to it. But when an electric stove gets hot, what color is it? Well, it starts to get more red, right? And it starts to emit. It's emitting other colors too, but red is the most dominant color. And if you were to get it even hotter than that, it might start to glow white. And if you get hotter than that, it might start to glow like a blue. Right, so hotter objects emit more light at all frequencies, but also hotter objects emit photons with more energy, right? So not only are they emitting more light, but they are emitting light that is more energetic. And that's why, our bodies, what's our temperature? Shoot, I can't even think of the conversion from Fahrenheit to Celsius. What are we, like 400 Kelvin? Oh, 310 Kelvin. It's literally right in front of me. So we're 310 Kelvin. We are not particularly hot. So we emit very low energy photons, like infrared. Infrared is a very low energy kind of light. But if an object gets hotter, it can start to emit visible light, which is higher energy. And if it gets even hotter, it can start to emit ultraviolet light, which is even higher energy than visible or infrared. So the hotter something is, the more light it's emitting and the higher energy light it's emitting, right? Okay, so take a look here. Notice how for all of these objects, the shape is the same, right? It's sort of like the curve is kind of steep on the left side and then more gentle on the right side, right? It's a more gentle slope on the right and a steep slope on the left. And the peak of this curve is sort of like skewed to the left side of the curvature. What I want you to take a look at here, I'm going to draw on this image with my pen. I'm going to do this for the red curve. Notice how the red curve has a line pointing to it that says 3000 Kelvin star. Right, so this is the curve for a star that has a surface temperature of 3000 Kelvin. Let's go look at the peak. Right, based on its temperature, the peak lines up with about 1,000 nanometers for wavelength. So the peak wavelength of this kind of star is in the infrared. Does that mean that it doesn't emit visible light? No, it just means it emits less visible light than it does of this particular kind of infrared. You can see how the intensity of the infrared is higher up on the y-axis than the visible light. Hold on, why is this not letting me erase? Oh, Shift E. There we go. But then you can take a look at the, then you can take a look at the yellow one, right? The yellow curvature, and the peak wavelength. This yellow curve is for the sun, which is hotter, 5,800 Kelvin. So you'll notice that it's emitting more light per unit area. So if you look at the red curve and then you look at the yellow curve, you see how the yellow curve is higher up. For any given wavelength, the yellow curve emits even more light, even if it's just that extra little bit. Right, so not only does it emit more light per unit area, but it also emits these wavelengths right here, which the red curve does not. Right, and that's sort of the second law here, that hotter objects emit photons with higher average energy. So in any case, let me go back to this for a second. So we have the sun. The sun's peak wavelength is somewhere around here. Right in the middle of the visible spectrum. Right, the sun's, the wavelength that the sun emits the most of is smack dab in the middle of the visible light spectrum. And we're going to get to why that's important in just a second. And then you have this 1500 Kelvin star, which is way hotter, almost 3 times hotter than our sun, whose peak wavelength is in the ultraviolet. Now, what does that mean? Does that mean that, you know, this 3000 Kelvin star whose peak wavelength is in the infrared, does that mean we can't see it because its peak wavelength is in the infrared? How about the 1500 Kelvin star? Can we not see it because its peak wavelength is in the ultraviolet? Right? Our eyes can't see infrared. Our eyes can't see ultraviolet. So can we see these stars? The answer is yes, we can. Right? We can see these stars. Well, then what color would they appear? Well, this is where the chart comes in handy. So let me erase and then draw again. Okay, so you see how the curve for the 3000 Kelvin star, the red curve, cuts through the visible light spectrum? We all see that? Hold on, where's my chat? Okay. Ian, sorry, I'm just now seeing stuff that was in the chat. 0 Kelvin is not 0 degrees Celsius. They are not the same thing. 0 Kelvin.
I knew that fact.
Okay, just making sure. Yeah, 0 Kelvin is like negative 273.15 degrees Celsius. It's very different numerically. Okay, sorry, back to this curvature. So the red curve for the 3000 Kelvin star, its peak wavelength is in the infrared, but it still emits visible light. And of the visible light that it's emitting, which color of visible light has a greater intensity? Well, you see how the red side is higher up than the violet side and the blue side? That means that this particular 3000 Kelvin star is emitting more red light than it is blues and purples. And so this star appears red to our eyes, not because it's not emitting blue or green or purple, but because the reds are emitted the most strongly. And if all other things were equal, if all colors were emitted at the same intensity, what color would the star appear? I'm asking you all that question.
White.
It would appear white, right? And so if one color comes in with slightly more intensity than the others, that's going to be the dominant color of that object. So this star would appear red, but the 1500 Kelvin star, its peak wavelength is in the ultraviolet. And so it still emits visible light. Not only does it emit visible light, but it emits visible light with a greater intensity than the sun or the 3000 Kelvin star. But that being said, notice how the purples have a higher intensity than the reds, right? The purples and the blues. And so this 1500 Kelvin star actually would appear blue to your eyes, right? Even though the peak wavelength is in the ultraviolet. Is this starting to make sense? Sort of how we're going through this? Just talking through it, showing how the lines cross through the visible light spectrum help you. Okay, thank you, Mario. All right. So again, the peak wavelength depends on the temperature of the object. Like humans, our black body radiation curves peak in the infrared, and we are not hot enough to emit any form of visible light, right? But we do emit infrared, and that's why you could see somebody with a thermal camera, right? Because we're constantly emitting heat, right? That being said, when we look at the sky and we look at different stars, hotter objects like the 1500 Kelvin star will appear blue. Cooler objects like the 3000 Kelvin star will appear red, right? And so this is our sun's spectrum, right? And our sun is an approximate black body. And you can sort of see how this jagged line sort of follows the dashed curvature for an object that has a temperature of 1500 Kelvin, right? It's a pretty close match, right? So why doesn't our sun perfectly match the curvature of a 5800 Kelvin black body? Well, it's because there are things in our sun's atmosphere that are actually absorbing light, right? So first of all, the sun has an atmosphere, but also, so like the sun's an ideal black body and it's emitting a continuous spectrum. And then there's an atmosphere around the sun. Tatsuya, could you elaborate on that in the chat? What do you mean? If you could turn the mic on, I think that would be easier for the people that are watching this at home.
Right. So when you look at the frame with a lighter, you see the blue part and left part, right?
Yeah.
And the blue part is hotter.
Right. So on a flame, if you look very carefully, like at your stove top when you light it, the parts of the flame that are closest to the gas holes, I'm not really sure what they're called, that the flame is blue, and then as it sort of gradually comes up and leaves the burner, it gets like orange and kind of yellowish at the tip. Yeah, right, and that's just because it's getting cooler as it leaves.
Right.
Cool. And that's why the temperature. Yeah, exactly. So coming back to the solar spectrum, right? We have the sun, this big glowing star in the sky. It's emitting all colors, right? It's emitting all of them. It's a continuous spectrum, as Kirchhoff would say. But the sun has an atmosphere, just like the Earth does. And in the sun's atmosphere, there are elements, atoms, and molecules that, as the light from the surface of the sun passes through that atmosphere, some of the light gets absorbed by the atmosphere. Right? Some of the light gets absorbed by the atmosphere. And by the time it reaches our eyes, there are big dips in the curve, and that's what this is showing. Right? So let's move on. Right? Very specifically, certain curves, certain dips, I should say, in this spectrum help us to identify certain elements in the sun's atmosphere. For example, this dip on the bottom left indicates that there is calcium-2 in the sun's atmosphere. There are different kinds of hydrogen, right? Hydrogen delta, hydrogen gamma, hydrogen beta. Magnesium-1 is this particular dip. Sodium-1, iron-1, and or hydrogen alpha, atmospheric oxygen, atmospheric water, more atmospheric oxygen. So all of these dips, we know what they are, right? We know what the characteristic fingerprint is for each of these things. And when we look at the sun, we see all of these identifiers. And that's how we know what the sun's atmosphere is made of, even though we've never been to the sun's atmosphere, or we've never been to the sun.
Professor.
Yeah.
Okay, so I want to ask something about the colors. When we see the sun during the afternoon, when the sun coming down, there's sometimes turns, you can see different colors, like going down to kind of red, not red, but a
Yeah.
So
Goes from like a yellowish white to a red.
Yes.
So the sun's color isn't actually changing, right? The sun doesn't change color throughout the day.
It's only the.
It has to do with how the sun comes through the Earth's atmosphere.
Okay.
And we have a whole segment of this class dedicated to that question.
That's why we saw sometimes beautiful afternoons when the colors changing that you see. Yeah.
Yeah, like there are beautiful sunsets and sunrises where the sun is very red.
Yes.
And that is due to how the sun enters the atmosphere. We're going to talk about that. Okay. Thank you for bringing that up, Andre.
Okay.
So these spectral lines, right? What causes them? Why does the spectral fingerprint of hydrogen differ from that of helium, or from that of calcium or carbon or neon or magnesium or anything for that matter? Why do they have their own specific spectral lines? Well, to understand that, we have to look at the atomic structure of these atoms, right? And remember that the atomic structure is different for every one of them. Okay, so this probably doesn't make any sense. So I'm going to go ahead and I'm going to share my iPad for a moment, and then we will come back from my iPad drawing and look at this slide. All right, so let me just go ahead and get the iPad going. New share. Boom, 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 boom. Okay. So when we think of an atom, for many of us, we might have this sort of picture in our head where there's like a nucleus with like protons and neutrons in it. And then there are these sort of shells or orbital paths where electrons can orbit around the nucleus. All right, so there are these different orbital paths. And I want to introduce this idea, right? That an electron, when it's at this lowest possible level, I'm going to draw it in red. There's our electron, sort of zipping around the nucleus, whichever way it may be going. Maybe it's going like this around the nucleus, right? So there's our electron doing its thing. What if we gave the electron more energy? What would it do? Well, with a higher amount of energy, it would have to jump to a higher energy level, right? So in an atom, there are energy levels at which an electron can jump to. You can almost think of it like, imagine this. Imagine being trapped in a well. So here's a well, right? And the bottom of the well, the lowest possible amount of energy is called the ground state. And you want to try to climb out of this well, but there are only certain points where you can grab onto. Right? There are only certain places you can grab onto. An electron is kind of the same way, right? Inside of its atom, right? So you have an electron in the ground state, and let's say that we give it some energy. Right? Well, first of all, how do we even give it energy? Well, you have to shine some light on it. You have to hit it with a photon, right? So if we take some light and we hit it at this electron, it can get the electron to quote unquote jump to a higher energy level. So if the ground state is like the energy level 1, then this might be energy level 2, and that might be energy level 3, and 4, and 5, and 6, and so on and so forth. If you can get the electron out of the proverbial well, right? If you can get it to pass over this lip, then the electron is no longer bound to the atom. The electron is free, and the electron can go off and do whatever it wants. It can jump to a different atom. But as long as the electron is in this well, it is tied to this atom. It can't escape it. So to get the electron to jump from one energy level to another, you have to give it exactly the right amount of energy. So let's say the electron's here at the n=1 energy level, and we shine some light on it, okay, and we hit it with a photon, right? There is an energy level difference between n=1 and n=2. There's a difference in energy. But if the light that hits the electron has an amount of energy that's less than this difference, the electron can't jump up to like this midpoint between them. It can't exist anywhere in here, right? That's not an allowed energy state for this electron. So the only way that an electron will go from n=1 to n=2 is if it gets hit with a photon that has exactly the right amount of energy to make that jump. Right, so I'm just gonna make up a number. Let's say that this is the energy difference between n=1 and n=2. I'm just, ignore the units, we're just gonna use a number here, is 10. Right? The difference here is 10 units of energy. And we shine a photon that has 9 units of energy. The electron will just ignore this photon. It won't absorb it. It can't. It's not allowed to by this atom. But if we hit it with a photon that has an energy of 10, then all of a sudden this electron, oh, why won't it let me move it? It's weird. Then all of a sudden this electron will make the jump by absorbing that amount of energy. What if we hit it with more than it needs to make the jump? What if we hit it with 11? Well, the problem is that the electron can't just absorb some of the energy, but not all of it. It has to absorb all of the energy. So if absorbing 11 would put it here, it's not gonna like take 10 units of energy and then let the other 1 unit go. It's just gonna ignore all 11 units of energy. It'll ignore this photon entirely. So that being said, there are very specific photons that carry the right amount of energy to get an electron to jump between energy levels. And the difference in energy between energy levels is not the same. So like from n equals 1 to n equals 2, that might be 10. But n equals 2 to n equals 3, this change in energy might be 7. And this one from 3 to 4 might be 3. And this might be 1. And this might be 0.2. Like it's, you know, there are only certain kinds of photons that can be absorbed, right? Certain colors of light. Well, why am I saying colors? Because if you listen to earlier, the earlier lecture, we made a direct relationship between the energy of a photon, how much energy the light has, and its frequency. And the frequency determines the color / type of electromagnetic radiation. Right, so the frequency of the light ray is going to determine whether or not it's ultraviolet or infrared or microwave or radio wave or gamma or X-ray or visible light. And so again, there are only very specific colors that can get the electron to jump between these energy levels. Back to the PowerPoint. So when an electron jumps up to a higher energy level, it absorbs an electron. But when the electron comes back down from that excited state, from that higher energy level to a lower energy level, it has to release the energy. And so what happens is the electrons actually emit the photons that they absorb, right? They emit light as they come back down to the ground state. So what we're seeing here are the different possible jumps that an electron could make. So let's say that, you know, in thinking about the well that I had just drawn, you have an electron that's at the n equals 5 level, at the n equals 5 energy level. It can drop from n equals 5 directly to n equals 3, or it could go from n equals 5 directly to n equals 2, or from n equals 5 to n equals 1, or it could go from n equals 5 to n equals 4, which is not on here. And, you know, maybe it goes from n equals 5 to n equals 4, and then it goes from 4 to 3, and then from 3 to 2, and 2 to 1. Or maybe it goes from 5 to 3, and then from 3 directly to 1. Or 5 to 4, and 4 to 1. Or 5 to 4, 4 to 2, and 2 to 1. Right? There are all these different pathways for that electron to get back to the ground state. And in doing so, there are all of these different kinds of light that can be emitted. So every one of these lines corresponds to a specific wavelength and a specific frequency of light. And that's how we get these energy level, these emission line spectrums. Right, so that's that. But then we also have the absorption line spectrums, right? And for any given element, it's just going to be these same arrows, but in reverse, right? Because the atoms are only allowed to absorb certain photons with certain amounts of energy corresponding to the differences in energy levels. So that's why the absorption and emission spectral lines look like inverted. Okay. So if there are any questions there, I would imagine now is probably a good time to ask them. If not, we're going to move on. Okay. So what have we learned? Well, I'd like for you all to chime in and answer here by turning your mics on. Why are some stars different colors than others? How would you describe that to, I don't know, a younger sibling or a child or a niece or a nephew.
That one is hotter than the other.
Yeah, has to do with temperature, right? Stars are different colors because they have different temperatures. Well, what about the next question? Right? How do we know that some stars are made of this material and some stars are made of that, or combinations? Right? How do we know these objects that we've never been to, yet we know what they're made of? How is that possible?
Because of the radiation, and it shows up on the spectrum.
And therein lies our answer. Thank you, Mario. That's the study called spectroscopy, right? Which is the study of light, right? The study of spectras. Okay, very good. Okay, so now we're gonna switch gears a little bit and we're gonna talk about a specific phenomena associated with light. But it's not really just associated with light. It's actually associated with all kinds of waves. So sound waves, electromagnetic waves. And this process, or this phenomenon, is called the Doppler effect. Does anybody know, before I go to the slide, what the Doppler effect is? Wants to share out? Nobody's heard of it? Really? Okay. So the Doppler effect goes something like this. Let's say that you had a light source. All right, in this diagram, it's showing the motion of the source by taking snapshots at 4 different moments in time. So let me actually backtrack out of this for 1 second. Let me go ahead and draw this. I'm going to go back to the iPad. There we go. Okay, so let's say that you just had a source of light, like a light bulb, right? Here's your source. I'm going to center that on the grid. All right, that's as good as it's going to get. And this light source is emitting a very specific, or let's just say that it's emitting a certain color of light. Right, so what I'm going to do is I'm going to draw here these different wave fronts. And I'll duplicate that again. All right, so notice how all of these, so the wave fronts you could think of as like the crest of a wave. So maybe this is like looking at a top-down view of a ripple, of ripples in a pond, right? So maybe you like keep tapping the surface of a pond and you get these like concentric circles, these ripples coming out. And if we're tapping, or if we're tapping this at a constant pace, what we notice is that the distance between wave fronts, which should be the wavelength, is the same on all sides. All right, the wavelength is the same everywhere. Now, what if instead of our source being stationary while it made these waves, what if the source was moving in a particular direction? What if our source were moving to the right? Well, let's see what would happen here. Let me actually just remove these for a second. And I'm going to sort of grab those one by one. So at this moment, right, the source emits this wave. Let me make this a little bit smaller. Right, it emits this wave S1. And then the source starts to move over to this position, S2. And as it moves over, the initial wave that it created grows a little bit bigger. Let me see here. How do I can just grab this. That would be cool. All right, so it grows a little bit bigger. And then while at, let me put S2 over here. While at S2, it emits another wave. And this wave is going to be concentric. Around S2. And then our object moves a little bit over again to S3. And as it moves over to S3, the original waves from S1 still grows bigger. The wave from S2 grows bigger. And then here's our wave S3. And then again, our source moves over to S4. And as it moves over to S4, the wave from when it was at S1 grows bigger. All right, that's still traveling. That's still traveling outward. The wave from S2 also gets bigger. The wave from S3 gets bigger. And then we have our wave from S4. That's not a circle. All right, so our source here is moving to the right, but it keeps emitting waves at the same frequency as when it was stationary, right? So like if this source were emitting blue light, it's still emitting blue light, but it's now moving to one side. It's moving towards the right side of the screen. Well, what is that doing to the waves? Well, now what's happening is the wave fronts are closer together. Right? The wave fronts here are closer together, and the wave fronts on the back are farther apart. It's no longer the same on both sides. So if you're an observer, right, if you're sort of standing off to the side somewhere, looking at the light coming from this light source, well, if you're over here observing it, now from your perspective, as the source moves toward you, the wave fronts get closer together and arrive at a higher frequency. What that means is that if this is a source of light and it's moving towards you really fast, it can actually change colors, right? It can it can appear to be a different frequency than the frequency that's emitted when it's stationary. On the far side, not the far side, but on the left side, what if you're here observing the source move away from you? Well, now the spacing between the wave fronts has gotten bigger, right? So we could say, as the source moves away from, sorry for my chicken scratch handwriting, moves away from you, the wave fronts get farther apart and arrive at a lower frequency. Right? So this is something that we actually experience all the time. Like not with light, but we experience it with sound all the time. You ever notice how like an ambulance drives by or a fire truck or a police truck or something, it goes by, it has the sirens going, right? As the ambulance or the fire truck is coming towards you, it's going wee-oo, wee-oo, wee-oo. And then as it passes you, it goes wee-oo, wee-oo, wee-oo. The pitch literally drops because as something's getting closer to you, you're getting those sound waves to reach your ear at a higher frequency. But when when the ambulance or whatever is moving away from you, now the spacing between the waves coming from that ambulance are getting farther apart. Therefore, they arrive to your ear at a lower frequency. They arrive at your ear at a lower frequency, and you hear a lower sound. You hear a lower pitch. So the same thing happens with light, except the color changes. And we call this red shift and blue shift. So here, coming back to this slide, we have the source moving towards the left. The waves on the left side are sandwiched closer together. Therefore, they will arrive at this woman's eyes with a greater frequency. And the light will appear more blue than when it's stationary. On the opposite side, we have this man who is watching the light source move away from him. Therefore, the wavelengths get elongated, they get stretched out. And as they become longer, the light appears to get redder. And this again is called the Doppler effect. So I want to emphasize something, and I'll go to the next slide if anybody wants to just go ahead and copy this down. So just these are some examples of the Doppler effect. You know, when traffic or a highway patrol is like monitoring how fast cars are going to make sure to try to catch people going over the speed limit, they use a radar gun. The radar gun uses the Doppler effect to figure out how fast cars are going. So basically, they shoot radar or radio waves towards your vehicle. The radio waves get bounced off your vehicle toward the radar gun. If they're coming back towards the radar gun at a higher frequency, then that means you're moving towards the radar gun. And based on the frequency that the radar gun picks up, it can actually figure out how fast you're moving towards the radar gun. So basically, how much red or blue shifting happens helps us correlate that with how fast something is moving towards or away from us. there are certain animals like bats. Bats use the Doppler effect to see in a dark cave, right? They emit screeches and they listen for how their screeches get reflected off walls, right? If they hear that the pitch is going up, they know that they're moving towards a wall. If the pitch is going down, they know that they're moving away from a wall. And if the pitch doesn't change, then maybe they're not moving with respect to the wall. Which is all very cool stuff. And then tying that into the universe, well, when we look out at the sky, we notice that almost all of the objects, all of the galaxies are redshifted, meaning they're moving away from us. And this is sort of how scientists have come to figure out more about how the universe is expanding. Okay. So I just wanted to, again, emphasize that the Doppler effect, when we say that something is being redshifted or blue shifted, we don't literally mean that it's becoming more red or blue. What we really mean to say is that it's becoming higher frequency or lower frequency. And I'll point that out, like I'll help you understand why in a second. Take a look here. So if you look at the middle picture, this is showing the emissions, rather the absorption spectrum from a certain star because it has certain elements in its atmosphere. And this is it when it's at rest relative to us. But when the star starts moving towards us, it gets blue shifted. Everything gets shifted over towards the bluer part of the spectrum. The spacing of the lines relative to one another stays the same, but everything gets shifted towards this part of the spectrum. So when scientists look at patterns like emissions or absorption spectrum coming from objects, they're really looking for the spacing between the lines to figure out what it's made of. And then based on how shifted the lines are from where they would be if the object were at rest, we can figure out how fast it's moving either toward us, or if the lines are shifted towards the red end of the spectrum, hence redshift, excuse me, we can figure out how fast they're moving away from us. So here's an example problem. Consider this one. Right, so there is a hydrogen emission line, which when it's at rest, corresponds to a wavelength of 121.6 nanometers. But when we're looking at this hydrogen emission line coming from a star, we notice that it has a smaller wavelength, only 120.5 nanometers. So a 1.1 nanometer decrease in its wavelength. Right. Given that these wavelengths are in the ultraviolet part of the spectrum, if you want to Google electromagnetic spectrum, so you can look at the different kinds of EM waves all at once. That's a good idea. I would do that. So given that these wavelengths are in the ultraviolet, is this shifted wavelength closer to or farther from blue visible light? So something goes from 121.6 nanometers to 120.5. That means the wavelength is decreasing. Right? If the wavelength is decreasing, what's happening to the frequency? Can anybody chime in and answer that one? Andre?
I think it get lower.
So if the wavelength
Let me
gets smaller, if the wavelength gets smaller, then the frequency goes up.
And then- oh yeah,
They have-
yeah.
Frequency gets bigger when wavelength gets smaller, right? So that's number one. So this ultraviolet light is becoming even higher frequency. Does that bring it closer to or farther from blue visible light?
Would it bring it like further away?
It would bring it further away, right? It would bring it further away from blue visible light. And yet, right, even though it's getting farther away, we still say that it's blue shifted. Even though it's getting further away from blue visible light, we still call this an example of blue shifting. So, like I said, the names blue shift and red shift might be a little bit misleading. It's more about, are we going towards shorter wavelengths or are we going towards longer wavelengths? Right, because you can have a particular spectral line that's being red shifted that moves past red and into the infrared, right? And as it, as it moves even faster away from you, it might make its way into the radio wave part of the spectrum. So it's getting further and further away from red light, but that's still being called red shifted because the wavelengths get longer and the frequency gets lower. So how is this useful to us? Well, when we look at stars, we can actually determine, or we can use the Doppler shift to help us find extrasolar planets, right? Planets that are orbiting other stars outside of our solar system. And we do that by looking at the star that might have a planet orbiting it. And if the alignment of the star, if the plane in which it's wobbling is parallel to the direction that we're looking at it from, right? So like basically if it's set up like this, right, where the star is sort of going around and around, and at some point it's approaching us, like on this left side here, the star is coming towards us at that moment. And on the right side, the star is moving away from us, right? And so what we have here, when the star moves towards us, the light that's coming from it gets slightly blue shifted. And when it's moving away from us, it gets slightly red shifted, all right? So what would be causing that wobble? What would cause this star to wobble on its axis? Probably something that's orbiting it. And so if we can figure out how frequently the star wobbles, we can figure out how frequently the unseen planet completes its revolutions around the star. And based on how much wobbling there is, we can determine whether that star is small and close, or big and far away, or big and close, or small and far away. We can figure out a lot of information there, right? And so this is actually a really cool application of the Doppler effect, right? That this is one of the main ways that we find planets outside of our solar system. Very, very cool. So let's summarize what we've learned, and then we will call it an evening. And so the three basic types of spectra, we have continuous spectrums, we have emission line spectrums, and absorption line spectrums. Right, those are the three spectra which are referred to in Kirchhoff's laws. How does light tell us what things are made of? Well, every atom has its own unique chemical fingerprint or its own unique spectrum. And when we look at objects, we can look for those fingerprints. We can look for those specific spectral patterns in the overall spectrum coming from an object, and then figure out what elements must be in that object's atmosphere or in its or composition. So there's a lot of good stuff here. Right. How does light tell us the temperature of planets and stars? Well, the fact that all stars typically emit a continuous spectrum, coupled with the peak radiation, right, and sort of the thermal radiation laws of black body radiation that we talked about earlier, we can figure out, based on the star's color, what its peak wavelength would be. And from its peak wavelength, we could figure out what its temperature has to be. Right, so every different temperature objects have different peak wavelengths. Right? And so there's a way to correlate that. And last but not least, how does light tell us the speed of a distant object? Well, this is where the Doppler effect comes in. Right, so not only actually does it tell us the speed of distant objects relative to us, but it also tells us whether that object is moving towards or away. Right, so we can figure out, we can look at a galaxy or a distant star and say, okay, is that light being redshifted or blue shifted? Oh, it's being blue shifted, so it's coming towards us. Or, oh, it's being red shifted, so it's moving away from us. And then we say, oh, well, you know, based on the spectral pattern that I see, these are the elements that must be in that object's composition. And from there, we can figure out, well, then how much shifting are we seeing? How much red or blue shifting are we actually getting? And based on the amount of red shift or blue shift, we can determine how fast the object is moving towards or away from us. Right. So light is an incredibly powerful tool for astronomers when studying the universe. It is the gateway to understanding everything. All right. And with that, that is the end of our slideshow. So I'm going to stop our recording, and then I will take any questions that you may have about your specific problem sets or whatnot. And with that, thank you for listening and have a great night.